and all of those important things. So let's start off with talking about charge, because we're going to use that to understand what potential difference really is. So first of all, in terms of charge, there are three types of charge an object can have. It can be positive, it can be negative, or it can be neutral or have no charge. So when we talk about charge, we measure it in a unit called coulombs. That tells us how big a charge is. And we give it the symbol Q. So when we're using equations, when we want charge in it, we see the symbol Q. So quite often in everyday life, neutrally charged objects become charged through various processes. So in order to become charged, you essentially would need to add or remove electrons from something. That's typically how things become charged. There are a few exceptions to that, but that's a good general rule. So if you add electrons to a material, it becomes negatively charged. If you take electrons away, it will become positively charged. Okay. So the electric force is different to a lot of other forces. So the electric force can be both attractive and repulsive. So if two objects have the same charge, which is sometimes called like charges, they will repel each other. So if they're both positive, they're both negative, they'll repel. If they have opposite charges, they'll attract. So a positive and a negative will attract each other. Okay, so we say that a charged particle, an object that is charged, has an electric field around it. That's how it's able to exert a force without touching something. So that field has direction. So when we're drawing a field for any different scenario, the direction of the arrows of the field are the direction that a positive charge would experience a force. And I'll show you a few examples of that. So I've used the word electric field. What do we actually mean by that? Well, it's the region around a charged particle where another charge will experience an electric force. So if a charged particle has a field around it, if any other charged particle enters that field, it will experience an electric force, or the two particles will experience a force between them. Okay, so what we're going to do next is draw some fields around charges in different scenarios. So the easiest ones to draw are what we call point charges, or charges that occupy no volume. So these are what positive and negative point charges look like. So you can see the field lines are directed away from a positive charge, because a positive charge would be repelled by a positive charge. Whereas with a negative charge, the field lines point inwards, because a positive charge would be attracted to that. So that's how we draw those or determine those arrow directions. A more everyday, or at least an example that you come across more often, would be a conducting sphere and parallel plates. So those are something you could come across in a lab, for example. So a Van de Graaff generator is an example of a conducting sphere. So you can see that actually that ends up looking very much like the diagram for a positive point charge. And then we've got parallel plates where we've charged one plate positive, one plate negative, and you can see that the field lines point from positive to negative, because a positive charge would experience a force in that direction. Okay, so let's dig into this one a little bit more. So as I said, this conducting sphere is how we kind of model a Van de Graaff generator. So what happens is, on the outside of the sphere, we build up a positive charge. On the inside, we build up a negative charge. So you can see that outside the sphere, a positive charge would be repelled. So that's why we draw the field lines outwards. Whereas if there was a positive charge inside the sphere, it would be attracted to the negative charge. So again, that's why the field lines are in that direction. Okay, so I'm going to talk a little bit about a process called induction, because it's responsible for several things that you might see quite often. So induction is when you cause something to become charged by changing its conditions in some way. So that's quite a general definition. So let's have a look at an example. And a classic example is sticking a balloon to a wall. So the first thing is, what we typically do is we charge up the balloon, and we usually use friction to do it, and friction usually makes the balloon negatively charged. So typically what you do is you rub it on your hair and you use the friction to transfer electrons from your hair to the balloon. That's why it becomes negatively charged. But when we want to stick it to a wall is neutrally charged. So that's theoretically anyway, at this stage, the balloon should not stick to the wall, at least at the moment. Okay, so this is our scenario. We've got a negatively charged balloon and we've got a neutrally charged wall. So as we bring the balloon closer to the wall, what happens is we induce a charge in the surface of the wall. So the electrons in the wall are pushed away from the negatively charged balloon. That leaves the surface of the wall positively charged, and that's why the balloon is able to stick to the wall. So the balloon induced a charge in the wall. The surface of the wall is now positive, so the balloon is attracted to it and sticks to the wall using the electric force between them. So let's see an example of this. I'll show you a demo. So this is using friction to charge up the balloon. We're turning the balloon negatively charged. And as you can see, the balloon induces a positive charge in the surface of the wall, and it's now stuck to it using the electric force. Okay, so another common example is we can use a polystyrene rod to deflect a water flow. So again, let's look at how that works. So a starting point is exactly the same. We charge up the rod using friction, and again, the rod typically becomes negatively charged. But again, water is neutral overall. But the difference here is water actually has regions of positive and regions of negative charge. Okay, so what that means is the oxygen on water is slightly negative and the hydrogens on water are slightly positive. So what happens is the water molecule aligns itself with the electric field like this. So you can see the positive is attracted to the negatively charged rod, and the negative side is repelled from it. But because the positive charge is closer, the attractive force is greater, and the water is actually attracted to the negatively charged rod. So again, let's have a look at that. So I'm going to show you this using a balloon because I happen to be holding one. So let's put it near to a flow of water, and you can see that the water flow is attracted towards the balloon because of the positively charged hydrogens line themselves up facing the balloon, and then they're attracted towards it, and we can see we can bend water using that principle again of induction. Okay, so we've looked at charge, so let's now move on to look at current. So current is the rate of flow of charge. So we measure current in a unit called amps, given the symbol A, and the actual symbol for current is I, because it originally stood for intensity, in fact. So before you can get a current, you need a material with free electrons. So it's not enough that a material has electrons. Every material has electrons. They must be free, or sometimes they're described as delocalized electrons. So there are three different words we use to describe different materials. So if something's a conductor, what it has is a high density of free electrons, or a lot of electrons per meter cubed. If it's a material as an insulator, that means it has a very low density of free electrons. And then semiconductors are somewhere in between those two. Okay, so what examples do we have of those? Well, conductors, the three common ones to know about are copper, gold, and silver. Insulators are very common, but things like plastics, rubber, these are our insulators. Air is a particularly effective insulator. The best insulator of all would be a complete vacuum, though. And then finally, semiconductors, the most common ones you'll come across is silicon, but there are a couple of others that are less well known, but are used when you're building microchips. Okay, so we can link charge and current. So remember that current is the rate of flow of charge, or the number of charges that pass through a point per second. So essentially we get the equation I equals Q over T, and we can see that 1 amp is 1 coulomb per second. Okay, so when we're modeling circuits, we talk about two different things. One thing we talk about is conventional current, and the other one we talk about is electron flow. So the idea of conventional current is what scientists came up with when they didn't know what an electron was. They hadn't yet discovered it. So the scientists believed that current was the flow of positively charged ions. So conventional current flows from positive to negative because positive charges would be repelled from the positive side and attracted to the negative side. And when we label on a diagram with an I to show the direction of current, we're showing conventional current. Since this point, we now discovered electrons, and we actually know now that electrons flow from the negative terminal to the positive because they're repelled from the negative terminal and attracted to the positive side. And that's called electron flow, and it goes in the exact opposite direction to conventional current. Okay, so the final thing we can look at is electromotive force, which we can understand on the basis of our understanding of charge. So before we do electromotive force, we're going to understand what electric potential energy is and how we can make it bigger. So if two charges are the same, you can increase electric potential energy by moving them closer together. If charges are opposite, you increase electric potential energy by moving them further apart, because in both cases we are doing work against the electric force between the charges. So same charges do not want to move closer together, so if we move them closer together by doing work, we're effectively storing energy, and we call that electric potential energy. So we use a word often with circuitry called EMF, or electromotive force, and we talk about this when we're talking about power sources. So a power source, a battery or a power pack or something like that, is giving electric potential energy to charges. And a potential difference is when we're taking electric potential energy away from charges using a resistor or a light bulb, something like that. So these two processes are essentially the opposite of one another. So a battery gives them electric potential energy, a resistor, light bulb, etc. takes electric potential energy away from charges. So an EMF and a potential difference are both measured in volts. They're both the energy per charge, essentially, which we give the unit of volts. The EMF, we give the symbol epsilon, and then potential difference, we usually give the symbol V, or sometimes even delta V. So we can actually define what 1 volt, the unit of potential difference in EMF, actually is. It's 1 volt is 1 joule per coulomb, and what that means is an EMF source of 1 volt gives each coulomb of charge 1 joule of electric potential energy, and a 1 volt potential difference takes away 1 joule from each coulomb. So let's think about a battery first of all. So a battery works using a chemical reaction inside the battery. So what it does is it takes in electrons on one side of the battery and produces more on the opposite side. So we get no net change in the number of electrons in our circuit, because for every one it takes in, it pumps one out the other side. So total charge stays the same. And what happened, this process is happening continuously. So when a current is flowing from the battery, this process is continuing continuously, and that maintains a fixed EMF across the battery. So a battery will be a 1.5 volt battery or a 9 volt battery, and it will stay at that value pretty much the whole time. So that's an EMF. Why does an EMF cause current? So at the negative terminal, we said the battery is producing an electron. What that means is it's forced electrons closer together than they would like to be. So it's done some work against the electric force and it increased the electric potential energy. And because we've pushed them all close together, what they do is they repel each other, and that pushes charges around the circuit. And this process happens continuously, and you end up with charges continuously moving around the circuit. Okay, so the opposite process happens at the positive terminal. So we've removed an electron from the positive terminal. So we've actually pulled the electrons a bit further apart, and then that exerts a force to pull electrons around the circuit in the same direction. So we create a region of very low electron density, and that acts to pull electrons around as well, because it leaves it net positive. So the final thing we're going to look at in this is power. So power is the rate at which energy is transferred in electricity by a component. So we measure power in watts, and we give it the symbol capital P, so we can distinguish it from pressure, which is lowercase p. So there is an equation to calculate the power of a component. So we need to know the potential difference and the current. That's what I and V stand for. So potential difference is the energy transferred per unit charge, and current is the number of charges per second. So if we multiply current by potential difference, we've got current, the charges per second, and the potential difference, the energy per charge. We can see the Q's cancel out, and we get energy per time, which you should know is overall power, or a watt. So that's where that equation comes from essentially, but the power transferred by a component, potential difference times current. And once we've got an equation for power, we can get an equation for energy transferred. So the equation that we're using is power is energy divided by time, which means energy is power times time. We know power is IV, so we get an expression for the energy transferred by a component in a certain period of time, as long as we know the current going through it and the potential difference across that component. And that completes this video on current, EMF and power.